and also how to verify that the code that we shipped actually works. And finally, how to carefully roll out the code that we shipped, especially if it's a little dangerous. During the development process, we get lots of questions, or we have lots of questions about our system that don't actually smell like traditional production monitoring systems. They're about how people are using it and how what the performance baseline is. And all of these do rely on what is actually happening today, what our current user base is doing. Because not all interesting things are a problem, but they're not always going to show up in our dashboards, and probably almost certainly won't show up in our exception trackers, which means that we need to go seek out these interesting bits of knowledge so that we can do our jobs better, ship better software. Because a lot of these interesting things are hypotheticals. What if we shipped this code that had this performance improvement? Who does it affect? How does it affect them? What does normal look like? How will our code affect normal? Here are some questions that look an awful lot like traditional ops questions, right? Questions about load, latency, how much our capacity is based on something that we did to the instance type. But if we frame these questions a little differently, bring them a little bit closer to the development world, a little bit closer to what the user experience is or what the customers see, it starts to look a lot like things that we should care about also. Your nouns might be different. All of these examples talk about individual customers. They talk about string-heavy payloads. You might be shaking your head. But maybe you care about expensive Mongo queries or individual shopping carts, or you care about one country's payment processing throughput. I don't know. You know your business. The premise is the same. The thing that is often the most painful to debug, the edge cases that are most interesting to understand, are where there's that one outlier that you didn't expect, doing something unexpected, while the code was built for something else. So here are some examples of some tools that currently try to help developers and operators solve this problem. Some folks might label one side monitoring, some might label the other side APM, some might label one side for ops people, some might say these are for devs. And I say, these labels are the problem. By dividing this up, by labeling one side for one type of person and another set of tools for another set of people, when we're all on the same side trying to deliver a service to our users, we not only continue reinforcing that wall between ops and dev, we're literally giving them two different views into reality. Quick sidebar. Why are we using the word observability for all this? Well, observability formally is about the ability to understand the behavior of your system based on knowledge of its outputs. Informally, I think of it as, what is my software doing and why is it doing this? And the reason there's this movement towards a new word for this is that while I'm not here to brag on the word monitoring, the truth is there's a lot of baggage that tends to be associated with that word. It tends to involve things like CPU graphs, tends to involve defining the threshold that we deem acceptable and picking a number and then setting it, immortalizing it in a dashboard and watching it, making sure that our system is behaving within accepted bounds. And our world is getting a little more complicated than that. Our world is getting a little more complicated than this is good, that is bad, this number has to be below that other number. Instead, what we're trying to move towards is a system and our observation of the system as a living, evolving thing. As we write code, our understanding of what is normal, what is acceptable, should change, should evolve. And we should be able to, instead of being restricted to the previous questions that we immortalize on a dashboard, we should be able to ask new questions, be able to evolve that, investigate some specific customer segment that we didn't care about yesterday, but really matters today. All right, end of the sidebar. So tools matter. The data we feed into these tools matter. And our tools for understanding prod can't just talk in terms of CPU, memory, disk space. Not if the ops folks want us, the developers, to think in terms of what our code is actually doing in production. So breaking this wall down between works on my machine and the only good diff is a red diff has to come down. We're entering a world with containers, and microservices, and serverless functions, and this world has too many moving parts for one set of folks to be entirely responsible for what happens after the code that we ship hits production. We, the people who are writing it, need to start being aware, need to start owning that shipping process, that release process. The first wave of DevOps was all about teaching ops folks to code, automating their release cycles and embracing the sort of automation that we take for granted. But if that was the first wave, the second wave is going to have to be developers learning to own our code in production, getting us comfortable poking at production data, bringing our development environment closer to our understanding of production. And observability is how we get there. Looking, asking questions, and understanding how our log data on our local machine translates to the real world. So observability should be a core part of the development process. As the software is being built, not as it's being evaluated for reliability or being prepared for deploy. We need to be feeding as much useful information into our tools, and we need to be asking questions about them. As much as testing or documentation, understanding what our code does teaches us how to build better software, all the time. Observability isn't just about finding out when things are broken or how things are going wrong. It's for understanding your software as it is executing. So let's take a look again at this checklist and break it down into some more manageable stages. First, we decide what we're building, what we're fixing, what features to add. Then we're figuring out how to build it. Figure out, make sure it works on my machine. These are our automated tests, integration tests, unit tests, functional tests, et cetera. And then we make sure, after we ship it, that it actually does what we say it does. If it's a performance improvement, let's make sure it actually improves the performance. If it's a new feature, let's make sure that the customers that we expected to be impacted are using it. And then the watching is, okay, it seems stable, but let's keep an eye on things. Let's make sure that nothing untoward continues happening. And these first three, look at them. What currently informs these three things, if not data from production? Your fantastic developer intuition, a product manager telling you what to do. It might be one or both of these things. But I sure hope we have some real data coming in on how we can improve, how we expect to improve, and whether the improvement had the impact that we wanted. I'll run through these 5 stages and share some real-world examples of what using data in these stages might look like. So figuring out what to build or fix. This is almost the most boring case for me because there's no shortage of people, software, humans, telling me what I need to build, what we need to spend time on. Alerts, exceptions, people on Twitter. But data comes into play when we go through and we try to refine our understanding of it, right? When we go from, oh, goodness, latency is high, to, well, latency is high and things feel terribly slow for this segment of our customers on this endpoint when they run this type of request. When we're debugging or we're looking locally, we have all of these signals that help us understand what our code is doing, why it's doing that, what code path it's following. But in production, we only have the data that we happen to capture when it happened. And that's a good and bad thing, right? Because there are some things that can only be debugged, only be simulated, only be discovered in production at scale. And in the ideal case, we have all the metadata that we need. That data that we capture essentially lets us replay history, lets us figure out what actually happened, everything about that we would find in our debugger. Since most of us aren't in the ideal case, we don't start out there, the important thing that we need to keep in mind when we're building this, when we're trying to use production data to figure out what to build, is to make sure that we are flexible about adding data as we need it to understand how the code followed through. All right, I promise an example. Honeycomb is, at its core, a query engine. You send us data, we try to make it queryable within a second. And so if someone comes to us and says, my data's not showing up, this is a big problem. We're like, oh, okay, goodness, like, why? We talked to this customer showed up, we said this, one of our engineers had a theory. Maybe they're sending us, everything looks stable on our side, maybe they're sending us bad timestamps. Maybe something's blocked or backing up on their side. We didn't have that data to verify that. We sort of just had our intuition. But we were like, oh, okay, hold on. Let's add a field, let it run for an hour. And this field was, awkward name, event time delta sec. That basically measured the difference between the timestamp that the user meant to send when something happened on their servers and when it hit our API. And then we could visualize it. We could say, show me the average of that value over time. Immediately, we can see this kind of concerning sawtooth pattern. Something's growing, dropping, doesn't show up for any other customer. Might be something on their side. And at the bottom, we can see that these 4 lines all map up, each with one availability zone. So these are availability zones that our servers are in, and maybe one of their servers, or maybe their cluster is having trouble talking to one of our Amazon availability zones. Okay, well, let's get some more data, verify that. We'll throw in the 95th percentile because we're used to working with data and we know that averages lie. And immediately we can see this orange line, the worst case latencies for the worst case delay for data being emitted on the client side, arriving at our API, is way higher than any of the other ones. Okay, weird, but interesting. And if we throw in the 10th percentile, as well as the median, continues to tell us a story of differences in delays between availability zones. And this is an example of, okay, a customer came to us with a problem. Without data, we might have to come up with a hypothesis, write some code, deploy it, cross our fingers, hope that it fixed the issue. But by looking at the data, using it, we can actually figure out, hey, we don't need to make a change right away. And we can go back to their customer with a very specific, hey, we're seeing this behavior. We're seeing it localized and concentrated here. Let's talk it through. Let's work it out. This is a case of using production data to figure out we don't have to write software to fix the problem. There's a difference, though, between knowing what to build and then knowing how to actually go about building it. Understanding the potential impact of a change we're making is something that is especially ripe for letting us bring data into the decision-making process. By learning about what normal is, lets us figure out how far our fix or our change will deviate, will change the status quo for our current users. And I like thinking about this section because it turns what we're doing by instrumenting, by having our services output data about what they're doing, it turns that into almost debug statements for production. And you can use, and these debug statements are something that we can use while we're working on the final solution. While we have our actual logic in a branch, we can see, what would my logic have done? By having a flow where it's natural and lightweight for software engineers to add these diagnostic bits, we can make more informed decisions, deliver better experiences. And while our PMs might make their decision based on qualitative user interviews and, again, grand intuition, we're developers, we have access to prod, we can back this stuff up with data. The example I'll share here is very early in our lifetime. We sort of hand-waved our rate-limiting implementation. We used an in-process cache. We're like, oh, we'll figure it out later. Each server can now kind of figure out whether a request should be rate-limited on its own. And as our traffic grew, we could tell there was this suboptimal correlation between which server a request hit, which customers were impacted, which ones were being rate limited. So we were like, okay, it's time to spin up a shared cache, time to centralize, clean up this, check that, centralize that logic. But instead of just blindly making that change, especially as we are tuning the heuristics for how we wanted to do our rate limiting, we realized we could start capturing data in prod to simulate the logic we were about to ship, to see what that steady state behavior might be. So alongside the logic and the API server that actually enforced the old rate limiting, we rolled out the shared cache, and we were like, hey, under the new logic, would it have been rate limited or would it not? And then we could graph it, and then we could understand, yes, new rate limiting is more strict in a lot of places, and especially so for large spikes, which is exactly what we wanted it to be doing. And we had enough here to examine each case individually to really make sure, okay, here's a case where it's not behaving as we expect. Is this okay? And third, again, our customer focus. The ability to identify which customers would actually be impacted let us be more communicative and let us weigh them more in our development in the future. All right, verifying on my machine. Testing. Testing is great. How do we pick our test cases? How many folks have ever been in an interview where the question at the end of the question was, how would you test this? Okay, a couple hands. This is a surprising thing that I feel like should be touched on more in interviews, but that's another topic. Often, this again falls back to intuition, falls back to, I think these edge cases are worth testing, and thus I will immortalize it in my written test. Well, we could do that, or we could say, hey, what is reality right now? What are the things that are realistically in bounds versus not? This is a graph over time where the y-axis is how large these payloads are, how many key value pairs are in each blob that my API server is receiving. And so, yes, apparently the largest blobs have 500 key value pairs, but most of them are under the 50 column mark. Cool. Now we know what kind of reasonable bounds are, what we should make sure to test. And this also highlights kind of an inherent shortcoming of tests written by humans, right? Even if we use data in production to inform what our test cases should be, who knows what crazy things will happen next month, next year. Which brings us to verifying in production that your code is doing what you expect it to do. We love the phrase testing in production, and someone here is actually wearing a shirt that says, I test in prod. When we say this, it does not mean only testing in production. It is not an excuse to skip writing test cases. It is not an excuse to use your wonderful CI pipeline that you have set up. What it means is testing before and after production are things that are complementary and should happen in all cases. They're both necessary and cannot happen for all cases. When you know the answer to what should happen if I throw in a negative number into this function, if you know the answer, you should write a test case, and you can. When you don't really know what will happen if 500 people call this function at once? You could spend a whole bunch of effort spinning up a test environment that will let you simulate 500 customers all hitting it at once. Or you could roll it out very carefully and see what happens. Because ultimately, there are some things that you can only check in production, at real scale, on a real network, with real user diversity. And complex systems have an almost infinitely long list of almost impossible failure scenarios. And as our systems get more complex, again, microservices, serverless, moving parts, by adding more components and adding more dependencies, the number of potentially tricky interactions will only continue increasing. So rather than trying to predict and process and handle all of these incredibly rare, incredibly unpredictable failure scenarios, we should make sure that we find out immediately when something happens, and we have enough information to handle it when it does. Speaking of our favorite way to test a hypothesis, feature flags. Feature flags are one of our favorite tools to help us test in production. They make sure that we've got this change we're pretty sure will work, all of our tests pass, but we want to roll it out really carefully, maybe to a particular node, maybe to a particular customer, maybe to some other segment. in order to find out what our code's impact is in the wild. And this becomes really powerful when we can get smart about how we target that segment. And my favorite part about this approach is that it ties in really well to, this means that the testing in production gets to take advantage of the ephemeral nature of feature flags, right? And these ephemeral feature flags line up really well with these sort of ephemeral questions in development. Okay, I'm building this feature. I think it will do this. Does it? And at this point, I throw this up on the slide just because we actually take all of our feature flags, throw them on all of our like own monitoring events, our own dog food cluster, so that each time we add an experiment, each time we add a flag, we don't have to think. We don't have to say, well, I should create a dashboard comparing the before and after of my experiment. It just gets added along with everything. It's all right there, where all of our top-line metrics are mapped to the flags that I might care about at this point in time. One of our examples. While a lot of our feature flags are used for UX reasons, anytime we make changes to our storage engine, we try to be very careful about how we roll it out. And a while back, we made a change to our how we stored strings, how we compress strings and how we store them on disk. And it was intended to be to make things a lot more flexible, but it was very explicitly not intended to have a performance impact on writes especially. So, okay, twitchy change, something we wanted to roll out very carefully. And we decided to roll it out to particular data sets. And customers have multiple data sets. Each data set is on at least 3 partitions. So we wanted to target per data set rollout because it let us localize the impact if something went wrong. You know, we could say, okay, we'll start with a very low priority data set. And it also let us check the distributed case, right? This is something that would be harder to test if we rolled code out one node at a time. We really wanted to make sure that our new code would work across multiple nodes. So we picked these metrics, threw them up, not on a wall, just on our laptops. And this is checking the overall volume of writes, as well as the cumulative latency of the batches. And we were immediately able to take these metrics and break them down by, is this data set being impacted by this flag, or is it not? This graph's purple line, this dotted line in the middle shows us flipping the flag from 20% to 90%. This is actually a little bit past wanted to target one data set. And we can see the volume of writes in the experiment go way up, and the latency of both go way up, or go a little bit up in that bottom graph. So that was a concern, until we dug a little bit further, found, okay, there is a correlation between write speed and the size of the write batch. And if we break down by that as well, we end up with 4 lines in the experiment, not in the experiment, large batch, small batch. And we could find that, in fact, okay, we feel okay that our feature flag did not, in fact, have a significant impact on performance. It's a little of a strange case. If anyone is very curious, find me later. I can point you to a blog post that describes this in gory detail. Okay, and finally, the watch phase. I think everything is working, everything should be fine. Let's maybe preserve this in a dashboard or something to make sure that it continues being fine. And I almost didn't include this because, as we saw with the show of hands, people are likely already doing this. And this is something that, as young developers, we are taught. Monitor production by staring at dashboards, scrolling through dashboards, trying to find lines that change and figuring out why. Okay, but when we're trying to figure out why something changed, what is the #1 source of chaos in a system? Humans. Either users doing their user thing, or us, software engineers, software developers, pushing new code. And as such, this is one of the things that I have found to be absolutely necessary when I start looking at dashboards, when I look at anything that tries to tell me about the health of my system. I need to be able to line up what that means to what I have shipped, what I've impacted. state of the art for this these days seems to be like drawing a line on a graph saying this is when the code was deployed, or matching up timelines. But a line isn't enough often. I can't count the number of times either a deploy has taken an hour, half an hour, much longer than I expected, or there's one node stuck somewhere on some old build, throwing errors until I can figure out why. So first, when we're watching, when we're monitoring, when we're making sure that things are stable, the whole point is making sure that reality lines up with expectations, right? Okay, we expect the line to kind of stay stable. Why is it not? But we need to do so in terms that we understand. I mentioned that ops dev split earlier. If an ops person comes to me and says, hey, Christine, I noticed that CPU is high since you shipped that code yesterday, what's going on? I can't immediately tie that back to what I need to fix, how to translate that to the actual line of code that needs to be tracked down, reverted, whatever. What I could understand is someone coming and saying, hey, I noticed that latency really increased on that one endpoint for our most popular customer, or for our largest customer. That tells me not only, in the latest build, that tells me not only when in history to look for that change that maybe needs to be reverted, but also where and for which cases. Here's an example. This is the different lines are the different deploys, and we can actually see these deploys roll out, roll in, and you can see the switchover happen, and this makes it painfully obvious that apparently we have one build or at least one server. No, we have 15 servers that all have line at the bottom that don't seem to be getting new deploys. It's kind of strange. Maybe I'll look into it. And here's a more dramatic example. This is from when I was rolling out a storage engine change again, making a change to how they were talking to each other, a little bit nervous about what was going to happen, so watching our top-line metrics very carefully. And this is latency for reads. So query times shouldn't be impacted by this change. But I was watching, and they were. By breaking down by build, I was able to pinpoint the build that caused the query latency to go up. That confirmed that, yes, indeed, my change was in it. But so was someone else's. So was someone else's change to the storage engine. I was able to go to them, point it out. You can see where they reverted it. Everything was fine. And when you think about the sorts of observability tools that are targeted for developers or built for developers, they tend to speak our language, right? Language of builds and endpoints, and users. But those tools are often not flexible enough for ops folks. And so if we just start to remember to fold some of the nouns that matter to us, some of the vocabulary that matters to us, into tools that are flexible enough, we can share a view into the world, we can share the same view into the world, and we can both start to educate each other about what is production doing, how does this map back to the code. And that's how we bridge this gap. That's how we start thinking about what happens after prod. We form hypotheses, we add data if necessary, we query that data to validate or invalidate what we thought would happen, we repeat, or we take action. And so yes, in the end, the things that we deal with day to day may be different, depending on which end of the spectrum we're on, but we have to build bridges that build us together, that bring us together. Together, we will ask new questions about our systems. I especially liked this blast radius phrase, which came out of the mouth of an ops person, because apparently they think of code that we ship as having the potential to blow up, because they have to deal with it, and it's something from that side of the room. And the more we start internalizing that, the more we start taking that back and owning it, maybe it'll stop being a blast or an explosion, and it'll more be like ripples that are carefully controlled in a nicely walled-off environment. Okay, so Christine, we've gone through all of these different cases of what you can do when you have all this data there. How do we get from here to there? How do we get from maybe wherever folks are today to this wonderfully observable system without spending a month instrumenting all of our services? and adding new data. A few parts of this that I'll run through. These first three are all about getting data in, how to incrementally get our systems generating data in a way that we want, that is actionable, in kind of increasing layers of specificity. We'll talk about how the way that you think about interacting with that data might have to change. And finally, a new, beautifully developer-friendly approach to the whole space, which some of you may be doing already, but we'll get there. So, best practices for instrumentation, capturing context in a structured way. What this means is capturing metadata as the code is being executed. So ideally, we have everything in one place, ready for analysis. Ah, that's lovely. What's especially lovely about this blob of key value pairs describing an HTTP request to, I guess, a web app, is that we have not just how long the request took, 72 milliseconds, we also have, of those 72 milliseconds, how much time it spent in the database, how much time it spent rendering. And this is the sort of thing that makes it really easy later to do real correlations, to do real sort of cause and effect analysis when it matters, knowing that those three timers are co-located on this one request. Establishing a common set of nouns, consistent naming. We talked a couple times already about the nouns your business might care about, maybe customer ID, maybe shopping cart, whatever. But establishing that common set of nouns across your engineering team and kind of nailing a naming pattern will just make your life easier so that you're not trying to figure out why one person used app underscore ID over here, another person used app camel case ID over there, a third person used application dash ID in a third place. It helps future us not hate past us. And by making sure that these nouns map to a consistent set of metadata, hostname, customer ID, build ID, whatever patterns start to evolve in our debugging, it makes sure that whatever part of the system we're looking at, whatever problem we're trying to solve, we know which columns to reach for. Instrumenting from the perspective of what you can control. Okay, let's use, again, the standard web app as an example. By instrumenting our application, we can know a little bit about what arguments were sent to it by the user on any given HTTP request, some metadata about how the code was executing, where it was executing, and what was returned. But what about this database, this black box over here? What's happening in there? Yes, MySQL, Postgres might all be open source, but I'm not maintaining a fork just to instrument it. Well, okay. I can't get inside of it, but what I can know is what my application is sending to it, what queries it's running, where those queries are being run from. And I probably know things about how successful it was, how long it took, how many results were returned. And once we start to have a record of the inputs and outputs from the app's perspective, we can start to get an idea of the behavior of this black box and how my application impacts it. So in thinking about starting to instrument, we typically start asking folks to describe what their system does and what their unit of work is, where it enters the system. For our web app example, a unit of work is an HTTP request. Maybe that's different if you're managing a pipeline or some other sort of shaped system. What is your unit of work? And the web app, where does it enter? Ah, the HTTP handler. Great. That's where you start. That's where you put your first hooks in for capturing metadata baseline about your unit of work. And again, in the basic web app, that baseline for metadata for instrumentation is just what HTTP attributes are there. What is the standard way of describing that unit of work? Then identify metadata that will help you isolate unexpected behavior in your business logic. Great, we've got this baseline, let's set that aside. What makes your application interesting? What will help you narrow down certain causes, isolate issues when you're trying to debug something? This is things like, where is the code running? Okay, this one host is a T2 micro and everything is a beefy machine. This thing is, okay, this one machine is having a problem. It's what code is actually deployed. What is the build? Which feature flags are enabled? What version of code is running? Because it's sure not master. What metadata about our business will impact the flow of the logic? Again, maybe it's customer and shopping cart. Maybe it's state of the blog post, something. But these are the sorts of things that often impact like the fork in the logic in your code. Which code path will it go down? And finally, capturing things about the execution, like what is actually being executed. Things like what's in the payload? What are the timers? Which black box are you talking to? A couple battle scars from our past where we're trying to figure out why a solid 1/10 of our API requests are failing. And having information about which database cluster it's talking to makes it really easy to find out, okay, everything that's failing is talking to this one database cluster. That tells us where to look for the problem. And be willing to experiment. We talked about these sort of ad hoc ephemeral queries that we run not because we know something is wrong, but because we want to know something about the system, because we're working on a feature or we're working on a bug fix that talks about a certain part of the system. So be willing to add something temporary to just try it out. A lot of the examples that we ran through earlier all depend on a feature flag that will only live for a couple weeks. Some field that we had to add in parallel with the code being written. The simpler and smoother it is for us to add this sort of metadata on the fly, the more we're likely to use it when we're actually trying to answer questions. And the flip side, clean things up if they're no longer valuable. And accept that nothing is set in stone, least of all instrumentation. If the field isn't useful anymore, get rid of it. If it might still be useful, keep it around. Our API server instrumentation probably has somewhere above 100 different fields for every HTTP request and has like 15 different timers, because over the course of debugging this thing, we've identified, it's actually really useful to know that how much time we're spending JSON encoding, how much time we're spending talking to Kafka, so that we can debug things in the future. Okay, so to ground these concepts in reality, what is it like to actually try to migrate from maybe where we're at today, unstructured text logs? I'm going to talk specifically about log lines. As developers, I feel like it's still what we reach for first, and certainly what a lot of our libraries will output. So when migrating from something unstructured, first, pulling in those things that will help us debug and putting them in as kind of non-destructively as possible. This is our first step towards that common set of nouns. And especially if you're operating in a world where you're trying to make improvements without disrupting what folks are currently relying on, this is a great step because it can be purely additive. And this is the part where you want folks to start thinking about, okay, yes, I see the left-hand side is about a task timing out, but what metadata can I add to make this log line still useful out of context or by itself? What is the context that we would want to add to learn more about this, to dig in further? Second, start introducing a little bit more structure. It's usually possible to do this in a non-destructive way. Maybe ask around if folks are relying on a particular substring search. But most languages have really great structured logging libraries. Love Logos in Go, .NET, Serolog, I hear is great. Finding something that works for you and migrating slowly will set up good habits and set you up for being able to analyze your logs in a smarter way. And finally, starting to think about building up context rather than emitting checkpoints. Because log lines really are a bunch of checkpoints, right? It's, hey, this thing happened after this thing happened. But to get more out of our analysis, we're going to want to start trending towards bundling up these related log lines into something that maps to that unit of work that we talked about. Folks ask us as Honeycomb all the time how to correlate these disjoint log lines in a file, especially if they're interleaved. Our answer is usually, Well, if you're a data analyst, you've got lots of time and no access to the code, maybe the answer is better string processing and layers of MapReduce and self-joins. But if you're a developer, you've got access to the code. Best way to handle disjoint log lines is to make them not disjoint, is to put that context together, pull that context together at the source. So instead of emitting something for in queue, something for timeout, hey, consider passing the context through, passing identifiers around so that you can describe the amount of time queued, the amount of time until timeout, whatever, something that describes how the unit of work progressed. Yes, you'll have to pass some more context around. You'll have to pass some identifiers around, maybe through your function, maybe through helper functions. But every language has support for this. Go has its standard library context package. Java and Ruby have thread locals. It's worth it. How did the earliest developers use logs? They used their eyeballs, and eventually they used grep. But that was like 20 years ago, 25 years ago, right? Doesn't it make sense that as our software evolves, as our requirements for the software development process evolve, that the tools and the process for how we figure out what it's doing should evolve as well? Yes, you might be able to use your eyeballs and figure out when something happened, how often someone with example.com email address domain got emailed. But imagine trying to figure out frequencies or trends or deviations without twisting yourself into a pretzel, chaining together a whole bunch of bash commands to process these log files. Logs are easy for humans to read, and it's great. Makes sense when the volume of requests for any single program are fairly small, when it's running on your machine. But in today's production world, logs are no longer human scale. They are machine scale, and we need machines to help us make sense of them. As one of my esteemed colleagues says, search makes sense for logs. Search used to make sense for logs. Search makes sense for web pages, but there is no page rank for log data, and our search terms are necessarily evolving. And visualizations are becoming more necessary to identify those outliers, figure out whether it's a trend, an anomaly, how worried we should be. Because having machines help us make sense of that data means visualizing, means helping us use our eyeballs to pick out trends in a smart way rather than scrolling past log lines. Because imagine we're taking our web app, trying to figure out why things have gotten slow. Okay, well, fortunately in our log lines, so far we have all this nice metadata to work with, which customer it is, how long it took, a little bit about where this request hit. And this log line might be useful and help me in my development environment. It starts to scale really poorly when trying to figure things out in production, even when we're only handling a few requests per second. Instead, imagine being able to visualize the actual distribution of latencies. The x-axis here, again, is time. Y-axis is how long each request took. The color of the dot is how many dots fell into that bucket. And this right-hand side tells me, okay, within the last 15 minutes or so, requests have gotten much slower than usual. But beyond this visualization, what I can do is I can say, well, this cluster in the upper right-hand corner is what's interesting. Those requests are strange. Tell me more about them. With all of those fields that were captured in the log lines, tell me which ones are represented more inside that interesting square versus outside. Looks like one endpoint is adversely affected and one user ID. Interesting. Let me go dig in there. And I can do things like isolate which user it is. By getting our data in a shape where smart tools can take advantage of them, instead of relying on all these disjoint log lines and trying to grep across them, we can start to do really smart things like this that make it easier to figure out where to start looking, who some degenerate symptom is affecting. And finally, oh goodness. Yeah, another talk, all right. Folks are talking a lot these days about tracing. And they're talking a lot about them as something for distributed or concurrent systems. And there's, in fact, a talk in this room immediately after this about that. Yes, they're great for concurrent distributed systems. They're also great for any complex system, because for that side of the room, I'm known in here, believe it or not, some complex systems are monoliths. Sometimes it's just as interesting to trace inside a process to figure out what it's doing and why it's doing that. So let's say we start with these task logs that we've been looking at, and we've attached task IDs. It ends up not being so much of a stretch of the imagination to say, Christine, these things that you talked about earlier about building up context and rolling them up, I don't want to think about those at all. Let me instead explore tracing, and instead group these log lines by which task they were a part of, and clearly indicate that the enqueued line is the entry point of each cluster. Because the nice thing about tracing, or an interesting thing about tracing, is that a series of related log lines is actually quite a bit like a trace. Traces really are just structured logs that have a few magic fields that help tools create the structure, infer the structure and visualize them. They have a couple of descriptors about where the code is executing. They almost always have a timer that indicates this log line is responsible for this amount of latency. And they have some magic identifiers that help basically pull together the structure of the log lines. And so with all of these, you can take your log lines and create some structure, create a visualization, tie them together into a trace. So let's say we're trying to figure out how a particular service is behaving, maybe why something is slow, maybe why something is exhibiting some other behavior. We can start from our high-level query to visualize trends, find an interesting trace, and now we can look inside this one specific service, get all this wonderful metadata about what each of these function calls represented, and understand immediately the structure and the execution of our code. By identifying these business-relevant fields, establishing these common standards, and thinking in terms of aggregates and trends, there's a whole lot from these instrumentation and observability best practices that translate directly to making traces awesome, making working with traces be awesome. And if you're like, oh man, my engineering team is stuck in just using text logs. Some countries skipped landlines and went straight to cell phones. Maybe this is the leap that your team will do. Because tracing, observability, these are understanding tools. These are tools and a way for the code author to communicate the structure of the code, how it's behaving, to people who are just looking at the artifacts. And tracing is going to become commonplace. And so if it's the quantum leap that you need to get to understanding your production software, awesome, explore it. Instrumentation and observability shouldn't just be checkboxes for after you deploy or satisfy reliability check with the ops team. They are continual things we should be investing in to keep us grounded with what's normal, what's really happening. And by capturing more lightweight transient information in prod, we can be better informed, make better choices, ship better software. So our mission I'd like you to leave with: stop writing software based on intuition, stop backing it up with data, get a little more ammunition to argue with your PM about. Because software engineers, software developers have the most to gain from observability. By teaching our tools to speak our language rather than just ops language, we can reap all the benefits. Because observability should be a core part of how we build software, who we're building it for. And we have the ability to use data to ship better software, make the experience better for all of our users. Thank you. Sorry we're so close to the end of time, over time. I will be around for questions and before the next session. This is my contact information. My DMs are open. I will also be around the conference the next few days, so please come find me. I'd be happy to talk more about this or show you more examples. Thank you.